Good morning. My name is Micheel Wassouf of the company Energy House. In the first part of the presentation, I'm going to present the monitoring data for an EnerPhit certified school in Barcelona. I am a passive house certifier. And in the second part, Marti and Amado, also from Energy House, who will present a Hulk analysis, a comparison of the technical code for this refurbished building, which is already in use. As I mentioned before, the project was undertaken in 2018 in accordance with EnerPhit. It's currently in the certification audit process with the Passive House Institute. I would say that this is the first or one of the first public buildings to go through this process, hence the interest in looking at this work. At the bottom right, there's an aerial photograph of the overall structure. In grey, you can see the roof of the school that was refurbished in accordance with EnerPhit standards. And then in red, the annex, which is the kindergarten in the top section. This was not certified under EnerPhit standards because there were certain complications due to readings from the gas boiler, which gave the total gas consumption values, and we had to do a weighting exercise to calculate the actual consumption of the building. I'm not going to go into the solutions that were adopted for this building because it was presented at the Passive House conference in Perth 2 years ago. The first chapter will focus on CO2 and interior temperature in a standard classroom. We were fortunate to be able to study and measure CO2 and temperature data for a classroom before the reform work. This graph shows the results before the reform for the months of January to June. And we can see that particularly in the winter months, January to March, air quality in this classroom was poor in CO2 terms. The coloured bars, well, I'll just explain what they are. The orange columns that you can see here, if you follow the cursor, well, the orange, blue and dark red columns correspond to ID 3 and 4, in other words, poor air quality. And we can see that in the month of March, 30% of classroom hours presented CO2 concentrations of between 1,400 and 2,000 ppm, which are values which are clearly above those permitted in the new technical code. It's also true that as from the month of April, there's an abrupt change. Obviously, we're in the Mediterranean, very close to the coast, and in the month of April, spring begins, and not only the swallows come, but also children begin to open classroom windows. Air quality before the reform in the months of April through to June was very good. Most of the time, 70 or 80% of the time, air quality was very good in interiors. So there were higher concentrations of CO2. To the right, it's interesting to look at the comparison with the monitoring campaign that was carried out by the Passive House building platform 3 years ago, in which 2 state schools were monitored in Barcelona. The values were slightly worse in terms of air quality. 40 or 50% of the time, the quality was very good. So the average was generally better. So after the completion of reform work, the situation changed. In the monitoring program from September 2019 to March 2020, unfortunately due to COVID, school activity was halted, so we only have values up to March 2020. Nevertheless, CO2 concentration was good. 80% of classroom time had air quality below 800 ppm of CO2. 90% of the time, air quality was good or very good, and 10% of the time, CO2 concentrations were in the range of 1,000, 1,400 ppm, which is acceptable. So this indicates that air quality in CO2 terms had improved substantially. Now I'd like to move on to temperature. Before the reform work, for much of the time, temperature was below that stipulated in the technical code. For example, in February 2018, 80% of the time, the temperature was below 20 degrees. At the other end of the scale, at the other extreme, in the month of June, 70% of the time, the temperature was above 25 degrees. So the results are fairly poor in comfort terms from a temperature standpoint. This graph provides greater clarity. If we look at the previous graph, well, above 25 degrees, a range of 25 or 26 degrees, let's say, well, on this graph, it doesn't really give us an idea of exactly the temperature at which this was recorded. But in this graph, which provides a more detailed analysis of the temperatures in the 3 months of winter, from January through to March, we can see that temperatures, particularly in the month of February, which was a fairly cold month this year, well, the temperatures were very low. Interestingly, well, these are records or readings taken during classroom hours in this class. And for many hours in the month of February, temperatures were as low as 14 degrees or even 12 degrees or lower. And this coincides with the complaints from teachers before the reform work was carried out, namely that in certain hours or for many hours in the winter months, children and also the teachers would have to wear their winter coats during classes. And in the summer, well, perhaps the results were less spectacular if we compare the situation with before the reform. For example, June is obviously a hotter month compared with April or May. Temperatures of up to 31 degrees were recorded. And for most days in June, during classroom hours, temperatures were between 28 or 29 degrees, which are quite worrying. And this is the reason why the town council of Viladecans is really committed to achieving energy efficiency and asked us to perform this energy reform project. Unfortunately, we were actually able to not just do the project, but execute it. So, after the reform, we can see that in September 2019, during many ranges, temperatures were above 25 degrees. This is because solar radiation or protection against solar radiation in this part of the building had not been completed. The solar protection measures have been completed on the exterior now. And that's the reason why the result in September was not so good, with 68% of the time temperatures being above 25 degrees. In general, we have to say that in summer, as indicated in PHPP calculations, to achieve EnerPhit certification in this climate, you cannot install an active cooling system. For example, a type of air conditioning or water battery where active cold is injected in the building. because otherwise the frequency of, or the overheating frequency or result would clearly exceed 10%, established by Passive House as the maximum limit. Hence the proposal that is being presented to the Town Council. So hopefully, when school activity returns to normal, we hope to install a ventilation system with heat recovery and add a water battery with a heat pump, and in this way provide the building with cooling. We've observed that nighttime natural ventilation in these buildings does not work well due to the management of the building, and it's quite difficult to encourage people to open windows. It's probably something that would work in private homes, but in these type of buildings it's much more complicated to manage. In the other months, the temperature range between 20 and 25, which is good, is shown here in the green bars in the graph. Well, that was achieved between 92 and 99% of the time. In January, February and March, it's true that the results worsened, but we're still analysing this because we're not entirely sure why they're slightly lower. There may have been a change in the controlled ventilation system and its operation, and in the first year this has required ongoing action on the part of the Town Council to try to calibrate and improve the system. And at some point, certain operational problems have had to be resolved in the ventilation system, which is something normal in these type of tertiary buildings. This graph shows the curve indicating temperatures during classroom hours from September until March. And the graph also shows what I explained before, that in September temperatures of up to 27, 27.5 degrees were reached, and then they dropped in October, reaching a fantastic range of between 20 and 25 degrees. So let's now move on to the next image. Well, this is a graph indicating relative humidity in the building. And once again, between October and March, the values were fairly good, between 30 and 60% relative humidity, which are ranges permitted by regulations. In September, a high concentration of relative humidity was detected, but this is typical in August and September, particularly in coastal parts of the Mediterranean. So if you don't act actively, it's very difficult to control these values in a passive manner. Well, the second chapter of the presentation focuses on real energy consumption. Electricity consumption was measured in a standard month, in a typical month. This graph presents consumption levels before the reform, indicated by the blue bar before the reform, and the red bar corresponds to the results for energy or electricity consumption after the reform work. On the right, we have broken down the results for the red bar because we've separated electricity consumption of the ventilators, because we know that the ventilators may be operating 15 hours per day. Although the Passive House recommendation is always to limit these consumption levels and not exaggerate ventilation flows, they do account for a large proportion of total consumption of electricity in the building. Lighting was also changed to LED lighting, hence the reduction of 22% in electricity consumption, with an increase of 5% due to additional consumption of electricity. That's the reason why it's very important to work with ventilation equipment certified by Passive House to guarantee low electricity consumption levels. And this is the final image that I would like to show, which is heating consumption. This graph also shows very interesting results. We can see that in the years before the reform, which are the 4 bars on the left, for example, the main building, which is the light blue section of then the kindergarten, gas kitchen, and also energy distribution, and all of the data that have been broken down in this analysis. And it's interesting to look at the light blue bar, which corresponds to gas consumption for the main building after refurbishment. We can see that it's reduced from, I think it's 7,000 kilowatts hour, says the gentleman, an average of 80,000 kilowatt hours. It was reduced to 5,000, equivalent to approximately 400 euros per year consumption heating for this building. So according to our calculations, this is equivalent to a factor 10 rehabilitation for this type of building. So with that, I would like to hand over to my colleague Marti Amado. I'm not going to go into these figures in detail because I think we've explained these before. And now we can move on to the next chapter, which will focus on the Hulk analysis and the technical code. Hello, good morning, good afternoon, and thanks for connecting to this presentation. I'm very briefly going to explain a comparison that was performed in the simulation in this building with PHPP, Passive House Certification, a simulation that we did with the Hulk for the comparison of and the justification of this new technical code. Okay. We developed the model in Design PH, the idea being to calculate the shading pattern using this software developed by the Passive House Institute, particularly given it's important to shade these type of buildings. It's not so easy to perform these calculations manually. This tool allows us to recalculate these parameters for the building this year using this new software. I'm not going to go into the transmittance values of the project in detail, but I wanted to show you these Excel sheets which have been associated with the PHPP to verify compliance. As you can see, the limit established for a non-residential building, in this case it's 0.72, and the result of the thermal transmittance coefficient through envelope calculated through PHPP is 0.52. So in this way we're able to check solar radiation control required by the technical code and calculate the kilowatt hours of solar radiation per square meter of envelope. The limit is 4. The protection elements of this building give us 1.2 according to calculations. The results of this simulation are shown here on this slide. Demand of 15 kilowatt hours per square meter heating per year and 13 in cooling. This is calculated for standard heating gains on interiors established in the PHPP. Then we performed a second calculation using the non-residential tabs in the PHPP to verify internal heat gains with the operating profiles for large buildings, taking into account hours, lighting, equipment, operating profile, people. The results were different. Heating demand was down to 11, cooling to 16 square meter. And we performed the same simulation with the Hulk model. We used the Hulk model to justify the new technical code. You can't see the slats here, but they're modulated in the simulation. And the results with the Hulk were very similar to those with PHPP. 11 kilowatt hours heating, in this case slightly more, 17 kilowatt hours per year in cooling. In Hulk we used an interior load profile that was adapted to the calculation performed in the PHPP, and we established that load profile in all areas of the building. In other words, we used the Hulk to develop a single zone model. That's the reason why we got those results, and they were similar to PHPP. But this is actually a multi-zone building. Around the central patio, there's the communication area, and around that communication area, there's the classrooms in the school with high internal or interior loads when the classrooms are being used. So you can have peak loads of between 25 and 40 kilowatts per square meter at some times, and also low internal load areas, which are the distribution areas and the passage areas or toilets. So, since Hulk allows us to zone the simulation and establish these loads, the results obtained differ with respect to PHPP in terms of average interior loads, based on usage profiles, particularly in cooling. From 17, it increases to 24 kW per hour square meter. And this is a serious issue with PHPP in a multi-zone building. Increasing internal heat gains to test the building in the summer at energy demand level is important. And energy demand tests, which can be carried out monthly or even yearly, what the PHPP will never allow us perform a thermal load calculation in a multi-zone building as clear as this one, which is so different in terms of internal loads. And the PHPP is also something that cannot be used to use the climate system. But it may be useful to get an approximate idea of annual energy demand in a building, taking into account the increase in internal loads and also taking into account what was explained at the last conference. It was explained very clearly by Juan Postigo and Jessica Grove-Smith, who explained the tool that can be used to modify the climate file, taking into account the effect of heat, temperature in summer due to greenhouse gas effect. We're accustomed to using with files containing data extrapolated from 2010 backward. So in the case of internal loads and for adapting the conditions, we can be a little bit more precise in terms of modeling these buildings and analyzing performance in the summer. And we develop the same model to comply with H1 for the envelope at window or carpentry level, eliminating heat recovery. We can see that the overall transmittance coefficient was 0.65, close to the limit. And with this model, the results given by PHPP, 73 kWh per square meter, and Hulk, in terms of heating demand, 33 kilowatt hours per square meter. Well, they're very similar. So in this case, the internal heat gains profile used was the same. You have to have an idea of exactly how you simulate with PHPP and Hulk and try to come up with a realistic equivalent. But if we do this work well and correctly, if we're rigorous in our approach with both Hulk and PHPP when entering data, then the annual demand data will be very similar. I'd also like to talk just very briefly about the performance of the building in the summer. As Micheel mentioned, there were certain problems with the commissioning of the ventilation system. There were additional problems that were initially had to be overcome. The solar protection elements had not been installed for the summer, and the building was closed. Perhaps the system for controlling variable flow in the ventilation system was complex. Well, there were certain complexities in the startup of all of these installations. So ventilation was not operating in nighttime cooling mode. So the first year was perhaps not very satisfactory. We would have liked to have analyzed performance with passive measures in the building this summer, but we couldn't do that, obviously due to the COVID issue. In any case, next summer, hopefully, the direct expansion air post-treatment batteries will already have been installed, which were in the initial project. And even on the most complicated days in the month of June, well, we hope to achieve good performance in the building in classrooms with internal loads. It would have also been good to have compared this with passive measures, but once optimized. And we don't have the monitoring data for the active measures. Perhaps they weren't as good as they could have been, and it would have been good to have been able to explain these in this conference. And we hope to be able to present the monitoring data with an active cooling system on another occasion so that we can look at performance in summer. Thank you very much. With that, I would like to end this presentation. Thank you for your attention.